So we're starting chapter 2, which is, as you can see, science systems, matter, and energy. It's chapter 2, and it's a little bit all over the place, as you can see in the topics kind of covered here. So again, this is still a little bit of introduction. Starting off, the chapter mentions this little case study here with this little guy over here. If you might know, this is Easter Island. And it's a nice study in regards to what happened. So somebody sometime created all these statues, and there's not really a population that lives there anymore. Well, not really. There was some people there, but not a lot. So the idea or the thought is what happened is as the population was growing, they started using more resources, and the population continued to grow, and they're using more and more resources. And then they had kind of a negative feedback loop that they wanted more resources, so they were cutting down more trees to offer up as an offering to their gods. And this obviously did not turn out so well. So it was just a first nice little case study to take a look at how resources could be used more sustainably, which we learned from chapter 1. So, the nature of science. What we're looking at here, you guys are going to do quite a bit of this semester or year, is looking at how to construct an experiment, what are the parts to it, and how do we do it? So one of the first things we'll do within there is collect data. And actually from the very beginning, something we're going to do is have a hypothesis, which is a testable statement, which simply means that if I do this, focus if, then this should be the result. And then you, of course, you test it looking at the data and seeing if that supports your original thought process. But developing theories, models, and laws. So that's basically how we go about testing things in science. And this is the format kind of going through there, which we just kind of mentioned already. So theories and laws. They're similar, but a little bit different. And we'll look at that here in just a few minutes. We kind of see again the process in here. Science is a great method that we have because you can't just put something out there and say that's the way it is. The beautiful thing is this section right in here is that peer review. Everything you put out there, you may feel all good about yourself with some study, and then you present that information, and the scientific community will attack it, trying to prove it wrong in the hopes of having better science. And hopefully for you, your thought would be accepted. Then it moves on from there. And then someone else could test it some years down the road and possibly disprove it. But that's the idea of what we want in science. We want to have information which is as accurate and correct as possible. Scientific law isn't as widely tested as theory, but we just kind of accept that it's true. So for example, gravity. We don't run a bunch of experiments to see if gravity works. Every time we've ever looked at it, it appears that it's there and it's working. So we just accept it from all of our observations, that it is true and it is a law. Hypothesis. Going through and testing, you have these variables. What am I actually going to be looking at? And the most important thing is we isolate. We look at one single variable in our test. The difficult scenario with that is when we're talking about nature, very, very, very few things in nature operate in this manner, where we're just changing one thing. Nature is very dynamic, and there are hundreds or thousands of things going on at the same time. So just because you change one variable truly doesn't necessarily mean that the outcome that you see is truly the outcome you would have in nature, because there could be other things going on behind the scenes that are not accounted for. So reasoning, inductive reasoning. The idea with inductive reasoning is that I can use a lot of very specific experiments to come to some general conclusion. So the example the book uses is I could take a bunch of objects to the top of a building, different objects, and drop them, and notice that they all, drop to the ground. Therefore, I could make the conclusion that objects fall based on gravity. We could also run an experiment that says, okay, I think that all birds have feathers. And then someone could bring up various different birds, penguins, eagles, parakeets, whatever you like, and see that they all do have feathers. And we could make a deductive reasoning going from something very, very general, all birds have feathers, and then looking at all the specifics down the line to get to each specific generality. That, yep, birds do have feathers because I've looked at them all from the top down. Limitations in our studying. Well, inadequate data understanding can limit our understanding of results, so we just don't know everything, so it's difficult to come to a conclusion. Models. What do we use models for? We generally use them for things that are very, very small, which we can't see, so it gives us a better conceptual idea of what they look like. And we could also use them for things that are very, very large. Solar system, whatever you like. Things, again, that we can't see because they're too big. We can also use them for these if-then scenarios. So again, it helps us kind of find a path of thinking with something we can look at. Say, if I do this, then the result should be what I see here. And again, here's a graphic that kind of shows that if-then scenario, putting in water. And you can see the various locations that water could go. Feedback loops, lots of different ways we look at feedback. So I do something to a system, an environmental system, and I see some results. The first example we see here is with a positive feedback loop. So if I have a sloped terrain and it is not with much vegetation, you're going to have erosion. And as erosion continues, you're going to have less vegetation, and the erosion will continue and snowball. The next one is negative feedback loops. So if I start recycling, I'm going to need less material for, say, aluminum cans. If I'm recycling my aluminum cans, I have to do less mining to get aluminum for cans. So the more I recycle, the less. So it works against the idea of my mining for aluminum. And then you have these other ones that are not as directly related to that, but they are certainly related. Time delays. So the one the book gave an example of, which is a good one, is smoking. Smoking is a negative. So if I had all these negative effects immediately, I would stop smoking. But because sometimes it can take 10, 15, 50 years down the line between starting smoking and having negative effects, it's too late. So the damage has been done over that period of time. The other one is a synergistic relationship. So if we're going to continue along with this whole smoking thing, if you were someone that had some asbestos exposure, the smoking would have worse effects on you than it would to someone who was not exposed to asbestos. So you get a synergistic relationship. Say that 3 times fast. Which just means they're working together to make that effect more strong. Next one, again, this is a hodgepodge of information here with some chemistry. Some organic we're looking at here. Organic chemistry, we're primarily looking at things that have carbon in them. And then you get a couple of guys that kind of go along for the ride. This gets into, again, organic chemistry. So these are the main things we're talking about with organic chemistry. You can also have some hydrocarbons and some chlorinated hydrocarbons. We'll talk about some of those along the way. And some carbs, carbohydrates. Everything else is considered, or most other things are considered to be inorganic. Sodium chloride, water, inorganic. States of matter. You guys have talked about these probably since about the 3rd grade. You have your solids, liquids, and gases. We're all very familiar with those. And then you got these ones which we really never ever mentioned, plasmas. Yep, that's an example of some plasma sitting there. The sun is a big ball of plasma. Pretty much it's just high energy ions. There you go. Matter quality. We got a nice little graphic in here somewhere. There it is. High quality versus low quality. You have all these little examples here. Another one you can think of is just simply oil. For years and years and years, we've been using what I guess we could call high quality oil, petroleum oil, that we've gotten from places like Venezuela, the Middle East, the United States. But then more recently, that stuff is, we still get it, of course, but it's becoming in less and less supply. So we're starting to use more low quality materials. Fracking maybe falls into that category. But these oil sands up in Canada, northwest Canada, we're starting to go after those because it's a huge supply of petroleum. Problem is, it's very low quality, and then the environmental impact on it is really high. But the need or demand for oil is also very high, so we are going after it. Types of pollutants. Some things are degradable. Paper, very good. And if you look around, you can find what we consider plastic bottles that are 100% plant-based, and they are degradable. You have other things which are considered biodegradable. Over a period of time, they will break down. So those things are also considered acceptable or not as bad for the environment. And then you have some things that are slowly biodegradable, which is this nice little picture here. Back, I think, in the 50s, this child here is being sprayed with some DDT. You don't typically see this anymore. I'm not even sure why she's being sprayed with that. Maybe she's got lice. I'm not really sure. But again, you don't see that too much anymore. And then you have things that are considered non-degradable, which would be like heavy metal toxins, leads, mercuries. Those things are elements. They don't degrade down any further. They're stable, so they are always there, but they are pollutants. Radioactive pollutants. Well, this is actually, we're about 12 minutes in, so we've gone probably far enough for this first lecture. I'll take a break here, and we'll do another one here in just a few minutes.